Hey everyone, and welcome. Today we're going to talk about something that's basically the invisible engine behind our entire digital lives, data replication. Let's dive in.
Have you ever really stopped to think about it? You're watching a live stream, and millions of other people are too. Someone posts a comment, and you see it instantly. How does a single service possibly keep up with all of that, all over the world, without crashing or losing a single piece of your data?
Well, the secret, and it's a huge one, is a powerful idea called replication. It's actually pretty simple at its core. Instead of relying on just one copy of the data, systems make lots and lots of copies. This one concept is what makes all the high-speed, super reliable apps we use every day even possible. Okay, so you might be thinking, why bother? Why make all these extra copies? It sounds like a lot of work, right? Well, it turns out it boils down to two massive wins for any system that needs to operate at a large scale. Okay, so first up, reliability. This one's a biggie. If you only have one copy of your data and that one server it's on has a problem, well, you're out of luck. Game over. But with replication, if one copy goes down, no big deal. Others are just standing by, ready to jump in. And then you've got performance. By spreading copies all over the globe, you can connect to one that's closer to you, which makes everything feel way faster. Plus, you can spread out all the user requests among all those copies, so the system can handle a ton more traffic. All right, so this all sounds amazing, right? More copies, more safety, more speed. What's not to love? But, like with pretty much everything in computer science, there's always a trade-off. There's got to be a catch. And this is the big one. The moment you create more than one copy of anything, you suddenly have a brand new and honestly a massive problem. How do you keep them all consistent? If you update one copy, how do you make absolutely sure that change gets to every single other copy and that everyone sees the most up-to-date version? That right there is the fundamental challenge of replication. So to even begin to tackle that huge syncing problem, we first have to figure out where all these copies, or replicas as we call them, actually live. Because they're not all created equal. They exist at different layers within a system. You can basically think of them in three main buckets. You've got your permanent replicas, which are kind of like the original master copies. Then you have server-initiated replicas, which are copies made by the system itself to speed things up. And finally, client-initiated replicas, which are the copies that live really close to you, sometimes even on your own device. In this diagram, it just lays it all out perfectly. Think of it like a set of rings. Right there in the middle, you have your permanent replicas. That's the absolute source of truth. The data then flows out to the server-initiated replicas to get closer to where people are. And then on that outer ring, you've got the client-initiated replicas, which are basically caches on your phone or computer, making everything feel lightning fast. All right, so we know where the copies are. Now for the million-dollar question, how in the world do we keep them all updated? How does a change made in the center make its way all the way to the edge? It really comes down to two basic strategies. The server with the new information can actively push the updates out to all the other copies. Or the other way around, the copies can periodically pull the updates by asking the main server, "Hey, you got anything new for me?" And this is where it gets super interesting, because you see the trade-offs right here. With a push-based approach, the server has to do a lot of work. It has to keep a whole list of all the clients that need updates. But the upside is huge. The updates are immediate. On the other hand, if you go with a pull system, the server gets to be kind of lazy. It doesn't need to know who the clients are. But now the clients have to keep asking, anything new? Anything new? And there's always going to be a small delay before they get the latest info. Okay, so push and pull are the big ideas, the strategies. But how do systems actually do this stuff in the real world? That's where protocols come in. They're the specific rulebooks that make replication happen. One of the most common ways to do this is called the primary copy protocol. And the idea is really simple. You just make one server the boss. That's the primary. Any and all changes have to go through the boss first. No exceptions. Yeah, this visual shows exactly how it works. A client wants to make a change. The request goes straight to the primary server, the boss. The boss then turns around and tells all the backup servers, hey, you need to make this change. The backups do it and report back. Only after the boss gets confirmation from the backups does it finally tell the client, okay, we're all good. This makes sure every change is safely stored everywhere. Reading data is way easier, though. You can just grab it from whichever copy is closest. The primary copy model is solid. It's dependable. But you can probably see the problem, right? That one boss server can get totally overwhelmed and become a huge bottleneck. So what happens if you just get rid of the boss altogether?
And that question leads us straight to a totally different way of thinking: active replication. In this world, there is no boss. Every single replica is an equal, a peer. When an update comes in, it's sent to all of them at the same time, and they all work on it together. It's a much more democratic system.
But, this everyone is equal approach has its own tricky problem. Just look at what's happening here. A client sends a single request to an object, let's call it A. But since A is replicated across 3 machines, B1, B2, and B3, they all get that same instruction. Now, if part of A's job is to send a message to another object, C, well, all 3 copies are going to do it. So now poor object C is getting hit with the exact same request 3 times, which is not just wasteful, it could be seriously harmful.
So whether you've got a boss server or a whole bunch of peers working together, it all circles back to this one giant question: what does it really mean for all these copies to be in sync? Just how consistent do they actually need to be with each other?
Now, one of the gold standards for being in sync is something called sequential consistency. I know it sounds super technical, but the idea behind it is actually pretty simple. It just means that the end result has to be the same as if every single action from every single user happened one after another in some single, agreed upon order. Basically, everyone in the system has to see the exact same history of events.
And boom, this slide is everything. It shows you exactly what we mean. On the left side, everything makes sense. One process writes A, another writes B, then 2 other processes both read the data. They both see B first, and then they both see A. This works. You can imagine a single timeline where B was written, then A was written. Everyone agrees. But now, look at the chaos on the right side. Process P3 sees B, then A. But process P4 sees A, then B. They have completely different views of what happened first. There's no single timeline that can possibly explain both of their experiences. That's inconsistency.
And that kind of brings us to the big final question, doesn't it? Getting that perfect sequential consistency is really hard, and it can really slow a system down. So a huge question for anyone building these systems is, do you always need it? Is it really a big deal if your friend's like on your photo shows up a few seconds late, if it means the whole app feels buttery smooth? That trade-off between being perfectly in sync and being super fast is one of the most interesting challenges in all of modern computing.